Today we're going to be breaking down the NVIDIA Keynote address from their GTC event. So this video is going to be a little bit different because I want to focus on the business side of it. So they jump a bunch into the tech, but I'm kind of looking for like, what are the business implications out of this? Like what really is Jensen saying? Like what is the kind of direction that he's taken NVIDIA and how do they really see the world? So we're going to jump through some clips. We're going to talk about a few different things. So I hope that you enjoy and we're going to see kind of what some not really reactions because I've already seen it, because that's lying. But some different clips are. But to start, I want to really kind of start at the end of the video where he kind of talks about what the whole vision for the future kind of is, because I think it's great to start there and then work backwards. So we will pull up that first clip.
Five things. First, a new industrial revolution. Every data center should be accelerated. $1 trillion worth of installed data centers will become modernized over the next several years. Second, because of the computational capability we brought to bear, a new way of doing software has emerged, generative AI, which is going to create new infrastructure dedicated to doing one thing and one thing only. Not for multi-user data centers, but AI generators. These AI generation will create incredibly valuable software. A new industrial revolution. Second, the computer of this revolution, the computer of this generation, generative AI, trillion parameters, Blackwell, insane amounts of computing. Third, I'm trying to concentrate. Good job. Third, new computer creates new types of software. New type of software should be distributed in a new way so that it can, on the one hand, be an endpoint in the cloud and easy to use, but still allow you to take it with you because it is your intelligence. Your intelligence should be packaged up in a way that allows you to take it with you. We call them NIMs. And third, these NIMs are going to help you create a new type of application for the future. Not one that you wrote completely from scratch, but you're going to integrate them like teams. Create these applications. We have a fantastic capability between NIMs, the AI technology, the tools, NeMo, and the infrastructure DGX Cloud in our AI Foundry to help you create proprietary applications, proprietary chatbots. And then lastly, everything that moves in the future will be robotic. You're not going to be the only one. And these robotic systems, whether...
All right, so what's interesting about this is that they really kind of clearly paint out like what their 5 pillars are of the future, right? One, they're seeing this as a new industry, so looking at generative AI as a new kind of general purpose utility. And he says this earlier in the video that we'll jump to, but seeing AI really as similar to electricity. He makes a point to it, and there's another video from, I think it's Andrew Nee, where he talks about AI as a general purpose utility similar to electricity. The second pillar is that, you know, that new industry is going to need to be powered by somewhere. Their Blackwell platform, which is this new chipset that can do an insane amount of computations on chips. And then so we have the industry, so we're outlining that. This is kind of like their general purpose. We have a way to power it through the Blackwell platform. NIMs is the way to kind of like harness that power. So we'll jump into NIMs too, but it's basically a great way to make generative AI accessible in a very packaged way to like deploy it. And that could be deployed within your infrastructure, behind your walls. It could be deployed at the edge, whether that's in autonomous vehicles or in cell phones or others, but it is a really cool thing that we'll talk about more. NeMo and the Foundry, so ways to give a lot of tools to make all of this much more robust, so being able to fine tune and hone things. And then finally, like the larger vision, and we'll get into digital twins, but being able, and this is the big like robotics play, I think that's going to put NVIDIA really far ahead down the road, but being able to create replications of the physical in the digital so that you can begin to train physical AI in a kind of safe and robust environment. And I think that all 5 of these do come together in a very cohesive vision that, and if I had to sum some of this up, is that, you know, one, they see AI and maybe specifically generative AI as a general purpose utility. And then the second being that the future is physical AI, which is how is AI embedded into real world products that make them do all the crazy things that the sci-fi writers of the past wrote about. So this is the end, right? This is the end of the video. And so I wanted to start here just to kind of like give that holistic view of like what is NVIDIA really talking about, because the rest of the videos and kind of clips that that we'll go through kind of back into that. So we'll start with the first one here around, generative AI as a new industry.
Why? Why is a new industry? Because the software never existed before. We are now producing software, using computers to write software, producing software that never existed before. It is a brand new category. It took share from nothing. It's a brand new category. And the way you produce this software is unlike anything we've ever done before. In data centers, generating tokens, producing floating point numbers at very large scale, as if in the beginning of this last industrial revolution, when people realized that you would set up factories, apply energy to it, and this invisible, valuable thing called electricity came out, AC generators. And 100 years later, 200 years later, we are now creating new types of electrons, tokens, using infrastructure we call factories, AI factories, to generate this new, incredibly valuable thing called artificial intelligence.
So he explains here on the thinking around how AI, and specifically generative AI, can be seen as this new, completely new industry, right? And being able to generate value through intelligence, through the platforms, and being able to, and again, tying this back into the 5 vision points, NVIDIA wants to be a factory, kind of a physical manifestation to the digital around being able to create intelligence, whether that's through the actual chips themselves that power it, through a lot of the tools that they give you with the NIMs, through NeMo and the distribution channels, and then all the way to providing kind of the environments to train these models, and the idea that their currency of the future will be tokens and a la kind of intelligence. And what I found interesting about this point is that it really kind of it backs up what Sam Altman had said recently, that he believes that compute will be one of the most valuable and potentially scarce resources in the future, which is kind of wild to think about. And also, I don't want to say like a bit dystopian, but if you think about compute being one of the most valuable and not something like water or food, it can be a little mind twisting to look at it from that way. But I don't disagree, right? Like as we get to this massive gold rush around intelligence, and if we do get to some form of AGI soon, then really the compute side of the world is going to be the most kind of crazy grab that we have potentially never seen before in the history of our species, which is kind of wild to think about. But he also makes a really good point around something as well that we'll look at here around the difference. And this is something that you can see here around accelerated computing and why this new kind of type of computing compared to general purpose computing is important. And this is, I think, a helpful kind of point of view from a business side to think about.
General purpose computing has run out of steam. We need another way of doing computing so that we can continue to scale, so that we can continue to drive down the cost of computing, so that we can continue to consume more and more computing while being sustainable. Accelerated computing is a dramatic speed up over general purpose computing. And in every single industry we engage, and I'll show you many, the impact is dramatic. But in no industry is it more important than our own. The industry of using simulation tools.
All right, so I wanted to cover this just because you might hear accelerated computing start getting thrown around a lot now that they're talking about it, but it's been around for a while and it's really easy to think about. So as of now, we kind of categorize things into two different ways. One being general purpose computing, which are basically computers that are general purpose and designed to run a large range of tasks. And this is stuff like your desktop you're probably watching this on, or maybe your mobile phone that you're watching this on. This is the same as like mainframes and servers and tablets and really just general purpose devices. And these are all really great, again, at doing a wide range of tasks, but they're really bad at doing hyper-specific tasks. And accelerated computing is using kind of specially designed hardware to rapidly accelerate some of the processes that may kind of bog down a general purpose CPU. And so you can think of this as, GPUs as a great example. In the new Apple MacBooks, they have their neural net engine, which is a, kind of chip and architecture specifically designed to run a lot of parallel processes for AI. And, what Jensen's saying here is that, one of the big kind of pivots that the computer world is going to take, and maybe specifically from a manufacturing side, is going to be a kind of renewed, maybe not renewed, but a massive interest in shifting from general purpose chipsets and hardware into very focused and accelerated chipsets and hardware. So this is a great kind of thing to think about, and I'll try to find the clip here.
To create products. In this industry, it is not about driving down the cost of computing, it's about driving up the scale of. When you become accelerated, the install base of NVIDIA GPU, it's exactly the same infrastructure, cloud, in a library, a domain-specific, that their customers could do fluid dynamic simulation at 1,000 times scale. Basically, a wind tunnel in real time. Cadence Millennium, a supercomputer with NVIDIA GPUs inside. A software company building supercomputers. Design it, build it.
All right, so I can't find the
simulate
exact
it, operate it completely digitally.
part where he.
In order to do that, we need to accelerate
where he
an
mentions
entire
it.
industry. And today, I would like to announce that we have some partners who are joining.
And just here, I'm trying to find like the picture of the car in the background. So the thing that he brings up here, and one of the big areas when he mentions the Omniverse or the robotics, kind of at that far right of the 5 pillars, is around this notion of digital twins. Now, you may have heard of digital twins potentially during in the blockchain context, but when we say digital twins in the realm of AI and kind of what this accelerated computing is doing, is that digital twins is being able to accurately represent the physical world in the digital. And this can apply and has a lot of kind of profound impacts to a number of different things. Like, for instance, here he talks about being able to create a physically accurate digital twin of a wind tunnel, right? So being able to put in digitally created objects and then get true representations of how those things would react in the real world. And this kind of goes across a lot of different lines. Later in the video too, he talks about being able to do it in healthcare. So being able to represent amino acids and other kind of like compounds and building blocks to better identify new drugs and how those drugs may react in humans to help accelerate drug development and bring it out to the market sooner. You're able to do it to, being able to train self-driving cars instead of in the physical. You might be able to get a lot further using a digital twin kind of world for them to learn in before they go out. And this goes into, robotic arms for manufacturing, into, supply chain. And there's a lot of uses for it. But one thing just to note, because I do think it's going to be coming up more in the future, is around that kind of concept of the digital twin. Next, I wanted to talk about the Blackwell chip. So this was the second kind of main pillar of their 5 things looking forward. And I won't go too kind of deep into it, but I thought the animation was really cool and it's worth noting because it is part of it. Again, this is kind of the Blackwell chips, and it's a cool animation. kind of runs through all their chips, components of it. But the part that I thought was kind of funny was that it just shows it kind of building, right? So the chips on the boards and the racks and the cooling, the networking. That is what an AI brain is going to look like. And I couldn't help it because it always makes me think of this. See the resemblance here, minus Keanu Reeves in it. But so when we think about it, and you know, I've had times where it's like, what will an AI brain look like? I'm looking at it. All right, so we'll skip past the Blackwell. Like, again, if you want more technical information, there's a huge kind of section of this video, really kind of from 29 minutes or so all the way through probably 56 minutes, is just some pretty deep technical stuff. But again, for the premise of this video, we're more concerned about looking at the business side. So the other one too that he had mentioned before is looking at and trying to create this notion of an AI factory. And that's kind of one of the big areas that NVIDIA is looking to push into and really kind of pioneer. And he's got a great kind of talk track on that.
For generative AI. And in the future, data centers are going to be thought of, as I mentioned earlier, as an AI factory. An AI factory's goal in life is to generate revenues, generate, in this case, intelligence in this facility.
Yeah, I think that's interesting, right? He says the AI factory's goal is to generate revenue. And in this case, revenue is intelligence. And I think that that's a pretty interesting notion to think about, as intelligence as a digital revenue source, and how you start to kind of like measure that. And the reason that I bring this clip up and why I think that it's interesting is because of that kind of shift in thinking about what the value of one of these server farms or these AI server factories are, is that the whole underlying goal of them is to manufacture intelligence, like systematically manufacture intelligence. And that to me is a pretty kind of brain twisty thing to think about, but it makes sense to a degree, right? I'm just gonna be very curious to see how that starts to get, you know, kind of empirically measured in the future, and what that kind of means for scale. So the next clip here that I want to talk about is that, you know, Jensen goes through what kind of led to a lot of NVIDIA, like what really led to them investing heavily into the AI space early on, and what kind of some of that, what was the genesis of the generative AI kind of play. And now this is how he explains generative AI starting from his point of view. I'm sure that there's some people out there, if you go and Google it, it's going to start in a way different place, but I thought this was a pretty cool place to think about it, especially from a business standpoint, and really kind of understanding why it's so impactful, and like how do we get to the realization that this was such a crazy cool technology. And it starts with cats.
That's what happens when you don't rehearse. Hang on a second. Guys, that was going to be such a moment. That's what happens when you don't rehearse. This, as you know, was First Contact. 2012, AlexNet. You put a cat into this computer, and it comes out and it says, cat. And we said, oh my God, this is going to change everything. You take 1 million numbers, across 3 channels, RGB. These numbers make no sense to anybody. You put it into this software, and it dimensionally reduces it. It reduces it from 1 million dimensions, It turns it into 3 letters, 1 vector, 1 number.
Well, so just to step it back here a second in case people, because I think it's helpful to think about it, right?
Channels RGB.
It says
2012, AlexNet. You put a cat into this computer, and it comes out and it says, cat. And we said, oh my God, this is going to change everything. You take 1 million numbers, across 3 channels, RGB. These numbers make no sense to anybody. You put it into this software, and it dimensionally reduces it. It reduces it from 1 million dimensions, 1 million dimensions.
All right, so the reason that I want to back up here is because I think this is pretty interesting to think about. You know, when we see a picture of a cat and we think about, whoa, wow, that's crazy. Like, what do you mean? Like, so what? It can recognize it, but I think, and what he's saying here is that it's able to take 1 million numbers and reduce it down and to be able to understand and turn that into 3 characters, CAT. So why is that so? Why is that so cool? Is that so within on a screen, right? You've got a bunch of pixels, and this is how images get displayed. So if you're looking at a monitor, you know, it's got millions of pixels on it, and all these pixels can be like, you know, one of 3 colors. They can be R, G, B. There was a kind of a tense for a time where, you know, some of them may potentially be yellow. And each of these RGBs are expressed as a number in the format R, G, and B, right? So each one of these is expressed like that. And within that expression, it might look like, and these all range from 0 to 255, 0 to 255, 0 to 255, right? And so this, a little hard to do. This is the same. This is how this is expressed, kind of numerically, right? And so if you think about what a certain pixel might look like, you know, it might be 10, 170, and 85. And this represents just one of potentially, you know, millions of these little dots that are on your screen that make your screen glow, makes it turn into whatever colors display images, displaying me right now. And when you think about it in the string of numbers, right, like what the computer sees is basically just a ton of these, right? 39, 80, 93, 105, you know, on and on and on and on for 1 million places. And like based off of this number string, it's able to reduce it down and say, based on this string, this array of numbers, this is a cat. And so it's, again, I think it's kind of crazy to think that a computer can go from just looking at these numbers into saying that it's a cat. And that's what he's saying is like such an incredible moment. While it might not seem, as you and I like look at a picture of a cat, like, oh wow, that's crazy, of course that's a cat. You got to think about it as like, imagine I gave you 1 million numbers, comma delimited, and said, what is this thing? For a computer to be able to find those patterns and reduce it down is pretty insane.
It turns it into 3 letters, 1 vector, 1 number. And it's generalized. You could have the cat be different cats. And you could have it be the front of the cat and the back of the cat. And you look at this thing, you say, unbelievable. You mean any cats? Yeah, any cat. And it was able to recognize all these cats. And we realized how it did it. Systematically, structurally, it's scalable. How big can you make it? Well, how big do you want to make it? And so we imagined that this is a completely new way of writing software. And now today, as you know, you type in the word CAT, and what comes out is a cat. It went the other way. Am I right? Unbelievable. How is it possible? That's right. How is it possible you took 3 letters and you generated 1 million pixels from it, and it made sense? Well, that's the miracle. And here we are, just literally 10 years later, where we recognize text, we recognize images, we recognize videos and sounds and images. Not only do we recognize them, we understand their meaning. We understand the meaning of the text. That's the reason why it can chat with you. It can summarize for you. It understands the text. It understood, not just recognizes the English, it understood the English. It doesn't just recognize the pixels, it understood the pixels. And you can even condition it between 2 modalities. You can have language condition image and generate all kinds of interesting things. Well, if you can understand these things, what else can you understand that you've digitized? The reason why we started with text and images is because we digitized those. But what else have we digitized? Well, it turns out we digitized a lot of things: proteins and genes and brain waves. Anything you can digitize, so long as there's structure, we can probably learn some patterns from it. And if we can learn the patterns from it, we can understand its meaning. If we can understand its meaning, we might be able to generate it as well.
This is a really interesting and I think thought-provoking kind of line from Jensen. He said, if we can digitize it in its structure, then we can find patterns. And if we can find patterns, we can understand its meaning. And if we can understand its meaning, we can probably generate it, meaning anything that we can digitize, which is crazy to think about the number of options that we could, is that if we can digitize it, then we can potentially generate it. And when you think about it, Beyani mentions, proteins and all kinds of other stuff in brain waves, right? If we can digitize it and find patterns, it's kind of almost limitless potentially to where this tech can go. And it's going to be interesting to see it. But I'll play it a little bit more here before we move on to the next one.
And so therefore, the generative AI revolution is here. Well, what else can we generate? What else can we learn?
That was the hook on why, the whole title of this section on why generative AI is here.
Well, one of the things that we would love to learn is climate. We would love to learn extreme weather. We would love to learn.
Yeah, so he goes into some practical applications for it. This right here, as we mentioned before, is a great example of a digital twin, right? They made a digital twin of the Earth. I think that this one, though, is like hyper-focused into Singapore. You can watch the clip, though. I'll put links to it in the below. So the one that I'd mentioned before, too, that I do think is pretty interesting.
Screening for new medicines is a computationally intractable problem. Existing techniques can only scan billions of compounds and require days on thousands.
So this is their clip on using generative AI within healthcare. And it is interesting, right? Because the whole...
Using NIMs for protein structure prediction.
Because their whole kind of shtick on it here is being able to find new drugs faster, being able to test them in a digital twin environment. But the question that I have around all of this is that if that's the case, right, in theory, this should drastically reduce the amount of the cost of drugs and let us be able to offer it out to everyone in some degree. But I'm going to be curious to see if this only increases profits of drug manufacturers or of this cost savings through leveraging generative AI in the digital twins environment actually does get passed on to the end consumer. But this is going to be a major area of investment as far and research and growth for AI is going to be in the healthcare side. We've already seen some stuff around having a digital nurse. They go through an example here where they've taught one of their NIMs or these kind of micro models on all of the Hippocratic documentation. I'm going to butcher that. I'm not a doctor and have ever been close to being one. Get very squeamish, but apparently they trained this whole model on it so you can go and talk to it, and it actually is extremely good. But okay, so the next big thing to is around the NIMs. So they spent a lot of time talking about this, but NIMs is NVIDIA's inference microservice. So we'll watch what he has to say here.
To you what it is. A NIM, it's a pre-trained model, so it's pretty clever. And it is packaged and optimized to run across NVIDIA's installed base, which is very, very large. What's inside it is incredible. You have all these pre-trained, state-of-the-art open source models. They could be open source, they could be from one of our partners, it could be created by us, like NVIDIA Moment. It is packaged up with all of its dependencies. So CUDA, the right version, cuDNN, the right version, TensorRT, LLM, distributing across the multiple GPUs, Triton Inference Server, all completely packaged together. It's optimized, depending on whether you have a single GPU, multi-GPU, or multi-node of GPUs, it's optimized for that. And it's connected up with APIs that are simple to use. Now think about what an AI API is. An AI API is an interface that you just talk to. And so this is a piece of software in the future that has a really simple API, and that API is called human. And these packages, incredible bodies of software, will be optimized and packaged, and we'll put it on a website, and you can download it, you could take it with you.
All right, so there's a few things here that from a business perspective, I think is really, really interesting. So NIMs itself, right? So it's this ability to kind of like package up AI. And I think that this is really, really interesting because one of the big questions today is that how do you really kind of deploy AI at scale? And how do you deploy it maybe perhaps in your enterprise environment in a way that actually is kind of cost effective, that you can replicate, pipeline and deployment processes around it. And NIM seems to be a great way to do it. And when they say they've packaged everything up here, what they've done kind of essentially, right, is that they've kind of stuffed everything that you would need to run this model into a Docker-ish style container that you can just deploy and be like, okay, here's an AI model, go throw it out there and start running. Really similar to like how cloud computing took the big leap when you could just kind of like on demand spin up a new server. You can now just kind of instantly deploy a new pre-trained model. And I think that this is going to have a ton of impact when we think about where the scaling portion of AI is going and kind of how you're going to start to see the influx of these large models being condensed down into smaller, much more focused models, which they call either small language models. This kind of plays into like the mixture of experts to a degree. Edge AI, meaning being able to deploy AI kind of containerized at the edge, whether that's in vehicles, that could be in your refrigerator, it could be in a lot of places, but having them already take this up and put it together and have it run on top of the existing CUDA cores is kind of wild, because it means that they already have, like everyone already has the hardware and the infrastructure out there to run it. You can just kind of press a button and go. You don't have to update your data centers or update any of your server racks to support this. You don't need Blackwell and the new chips to do it. It all runs on what's out there, which is really kind of insane to think about, to be able to deploy something of this complexity and compute needs onto existing cores and have it run effectively, which I say run effectively. I didn't see any performance metrics on the NIMs itself. I don't think in this video, but it'll be interesting to see how well they run. If they run great, like that's kind of cool. And he mentioned another thing too here, that, an AI interface or an API is that you just talk to it. And he said it really well, that the API of the future is called human. And I think that's brilliant, right? The natural language future of being able to just talk to these models or talk to technology and be able to surface what you're needing rather than a typical search method is a pretty profound change in how we approach, how we view, how we architect, how we design, and how we integrate software throughout not only enterprises and business, but into the commercial and kind of personal lives. So the next one here that I want to jump to is, how do we build software in the future?
Just be in a NIM, and you'll assemble a whole bunch of chatbots, and that's the way software is going to be built someday. How do we build software in the future? It is unlikely that you'll write it from scratch or write a whole bunch of Python code or anything like that. It is very likely that you assemble a team of AIs. There's probably going to be a super AI that you use that takes the mission that you give it and breaks it down into an execution plan. Some of that execution plan could be handed off to another NIM. That NIM would maybe understand SAP. The language of SAP is ABAP. It might understand ServiceNow. And it go retrieve some information from their platforms. It might then hand that result to another NIM who goes off and does some calculation on it. Maybe it's an optimization software, a combinatorial optimization algorithm. Maybe it's just some basic calculator. Maybe it's pandas to do some numerical analysis on it. And then it comes back with its answer.
All right. So basically, you know what, I agree and I disagree with this, this idea. And he said to string together a bunch of different chatbots to be able to go kind of accomplish some task. That definitely will be a thing. That idea of stringing together multi-models is called a mixture of experts. And what it allows you to do is basically leverage specific models kind of or orchestrate multiple models, each one being very good at one thing or maybe some subset of things, to take a really, complex ask and effectively answer it. So, in the case here, and what that's a lot of times driven by is that you can see this top level model. I always forget it. I can't remember if they call it like the distributed model, the orchestrator, or the broker model. But basically, when you ask it a question, it is this top level model's job to say, okay, great, you're asking me to get you a cake. Let's say it's a really bad example. But in order to do that, I need to be able to find local restaurants and see which one's the best and also which one serves cake. So that might be one model itself. It might also need a model like, okay, I need to be able to call them and relay an order. So you might have a really good model at doing text to speech. You might need some model that's able to do brokering and paying. I don't know. You get the point, right? So it's that you use these multiple models kind of in harmony to be able to take a complex problem and break it down. And that definitely will be a thing. Not arguing that at all. Where I disagree, however, on that you won't be writing code is that I don't know how that mixture of experts type of thing, given current kind of compute cost, is going to scale, right? Will it work well for like one-off type of needs where you're asking it something that's very, I don't want to say personal, but unique and maybe a single instance of that problem? Will it work great for that? 100%, right? But if you're have a task that might be done by thousands of different people simultaneously and it's repetitive, right? Meaning that this same task it will get done over and over, such as potentially pulling data from, showing data in a dashboard. Doing this is just overkill, right? Like it is driving an 18-wheeler to the store to get groceries. You don't need that much horsepower to do it. Writing code is a great way to get hyper efficient for these very repetitive tasks. And there's a lot of those, right? Like there's a lot of those in enterprise. There's a lot of those in the commercial space. So do I agree that we won't be writing any code in the future? Absolutely not. But will we be really drastically opening up what is the definition? How do we solve problems using technology now that we're not pigeonholed into using specific applications that have already been written? And I think that's kind of a big jump, and is going to be a really interesting field of human-computer interaction, which is a whole discipline of software on how people interact with technology. And I think that's going to be a really, really cool place to see kind of expand over time. Next one here, I do think is good for businesses as well, because it
platform in
talks
the world
about
that has valuable tools that people use is sitting on a goldmine for co-pilots, and they would like to build that has valuable tools that people use is sitting on a goldmine for co-pilots, and they would like to build their own co-pilots and their own chatbots. And so we're announcing that NVIDIA AI Foundry is working with some of the world's great companies as
all right, well, the clip kind of
co-pilots
sucks, but,
using NVIDIA.
But what he's saying here is that basically the great thing that makes AI very powerful is data, and every IT organization out there is sitting on a gold mine, whether that's structured or unstructured data, to be able to effectively build and deploy these idea of copilots or NIMs, because all that data is there. Now, there's definitely going to be some, I think, learning curve in how that data gets actually curated and trained for these. They mention it here later, and I think that's the NEMO part of the presentation. But that idea that you're already sitting on everything that you need to do this new technology and transform in this way effectively is, one, reassuring, and two, kind of really begs to ask the question of, like, why would you not be doing this now? Like, why would you not start adopting this? You have everything you need. You just need to go implement it. It's not like we're asking you to start creating data. You do that on your own. And the other kind of next thing to jump to is the generalized human robotics clip.
They would like to build their own copilots and their own chatbots. And so we're announcing that NVIDIA AI Foundry is working with some of the world's great companies. SAP generates 87% system like DGX. We compress it into a large language model. Trillions and trillions of parameters become built semantically.
I put the wrong
Instead
thing
of
down.
the world being in, we build the robotic stack from top to bottom, as I was mentioned, from the computer system, but in the case of self-driving cars, including the self-driving car application. It could be reprogrammed, just as I showed you.
So what I was looking for in this clip, so robotics is kind of that fifth pillar for NVIDIA, and I think that this is like the big bet is that, they call it generalized human robotics, and that this is kind of the next big watershed moment for development. And what generalized human robotics is really starting to take, so robotics today is already out there. You've probably seen like the articulating arms that work on, that assemble cars. You've probably seen some baseline robotics that drive, maybe Amazon, has them drive around their warehouse to move racks. And this is all robotics, right? And even self-driving cars is robotics. But the human robotics is when we start building robots that kind of resemble the human form, so that they better integrate into our world, right? And this is important because our whole world was designed for humans. And I say the world, the manufactured world that we live in, not beautiful nature, was designed for humans, meaning that, if you think about it, doors, chairs, how we design houses, lay out buildings, build sidewalks, organize shelves at the store, your dishwasher, your sink, everything's designed around humans, and even oddly enough, primarily right-handed humans. And trying to build robotics that fit into that don't fit that kind of generalized human form makes it really, really difficult. And so this next big bet around, and for NVIDIA, is around this idea of generalized human robotics. He has an amazing kind of like Tony Stark moment here in a bit, which is like kind of cool. I thought maybe one day I'll be able to do this.
About the same size.
Skynet has entered the chat. Oh my goodness.
The
That's
soul of
crazy.
NVIDIA. The intersection of computer graphics, physics, artificial intelligence. It all came to bear at this moment. The name of that project, General Robotics 003. I know. Super good.
Engineer named it.
Super good. Well, I think we have some special guests.
Yeah. So anyways, again, this hits on that last pillar, right? Which is around it all. But just to recap, into is that there's kind of 5 areas, right? So one, they're seeing that there's this new industry, which is generative AI, and they see AI and really intelligence at its core as a general purpose utility similar to electricity. And it's really kind of breathtaking to think about what this is going to enable if you use electricity as a kind of measuring stick and what it enabled. The Blackwell platform, which are their chips and data centers to power all of this. NIMs is being able to package up the AI into kind of this containerized and easily deployable and therefore scalable and distributable AI fashion. NeMo and the NVIDIA AI Founder is how you actually are able to interact with these models really easily and be able to train them and fine tune them. And then finally, all of this kind of culminating into the Omniverse, which is the sense of digital twins and being able to replicate with near perfect accuracy the physical and the digital. And then what does that mean for the future of robotics and specifically around generalized human robotics? So creating these ways to teach these models and teach these robots much faster how to live and work and be beneficial within the world that we live in. So that's a breakdown of the NVIDIA keynote address. I'm a few days late getting into it, but I hope that this was helpful. Again, we tried to stay high level and we didn't want to get down into super technical. There's tons of that out there that you can go read, but I wanted to approach all of this from a business type of standpoint. So with that, we will see you on the next video.